Hello everyone. I hope all of you are doing well. So in the previous lecture, we just discussed about the EM algorithm for exponential distribution under interval sensing, where we developed the formula of EM algorithm for exponential distribution under interval sensing, where we developed the E step formula and M step formula. So the formula was E step formula was we have given that Ti at kth iteration was we observed that was 1 upon lambda value at kth iteration plus Li minus Ri minus Li divided by e raised to the power lambda's value at kth iteration into Ri minus Li minus 1. So Li, Ri and lambda raised to the power k we defined in the previous lecture. So corresponding the conditional expectation function, that is q lambda, given lambda's value at kth iteration was given, that was n log lambda minus lambda summation over the range of I goes to 1 to n ti at the kth iteration ti cap. All right, and corresponding m step was lambda k plus lambda value at k plus 1 iteration. It was n upon summation over the range of I goes to 1 to n ti cap at kth iteration. So in this lecture, we are going to solve a numerical example based on EM algorithm for exponential distribution under interval censoring. So now in the example, consider consider n equals to 5 subjects with interval censored observation is given such that the 5 observations are like between 0 and 1, between 1 and 2, between 2 and 3. We are going to take a very simple example here right now. 3 and 4, 4 and 5. All right, and take the initial value. Initial value of lambda, that is lambda naught at 0 iteration, is suppose 1. So since each interval has the width of 1, so we have, okay, I just write down that since interval has the width 1 we have Ti cap naught. We can calculate. The formula was this, so we can calculate the Ti cap while using this formula. So it will be Li plus 1 upon lambda naught's value is 1 minus Ri minus Li, that is the width of the interval, that is 1. So it will be 1 upon e raised to the power 1 into 1 minus 1. So when we are going to solve this one for each value of I, that is going 1 to 5, so corresponding T naught will be, before that we just calculate it, so it will be Li plus 1 minus 1 upon e raised to the power 1 minus 1. So after simplification we will get Li plus 0.4180 after solving this portion. Alright, this is the 0.4180 is the value of this portion. So corresponding values for each Li, that is 0. So it will be 0.4180. For second it is 1. So plus 1, that is 1.4180, 2.4180, 3.4180, and 4.4180. This is the value of Ti at the initial state. Take the sum of all these values, because in the formula of Q we have the summation Tik. Right. So their sum is summation over the range of I goes to 1 to 5 Ti cap naught is equals to 12.0901. Alright, when you are going to add all of them. So therefore, lambda 1's value will be, from the M-step formula, it will be 5 upon their sum, that is 12.0901. So it will be approximate to 0.4136 after dividing it. Alright, so that is the values of lambda 1. In the next term, so from the next iteration, we have Ti cap 1, that is Li plus 1 upon, now lambda 1 will change, lambda k will change here, it will be this value lambda 1. So that is 0.4136, right? So minus the width will remain same, that is 1. So e raised to the power 0.4136 minus 1. Now we need to solve this portion. So after solving this portion that you can solve by calculator by your own, so it will be Li plus 0.4656 approximately you will get. So their corresponding sum it will be T cap 1 equals to 0.4656 1.4656, right? 2.4656 and 3.4656. After that, 4.4656. That will be your T1's value. Then, sorry, not corresponding, some corresponding values. So their corresponding sum is basically summation over the range of I goes to 1 to 5 of T I cap 1, that is basically 12.3282. The sum of all these values. Okay. So now then lambda 2's value is 5 upon 12.3282. That will be approximate to, after dividing, 0.4055. All right. And so on. So till we will go further to find out the estimates of the different lambdas value till it is not going to be converged. So the EM algorithm replace unknown event times by their expected values under the current model. So in the interval censoring, this is the specific, especially useful because the exact event time are hidden and direct maximization is difficult, and EM gives a simple iterative update, and the method use all partial information efficiently. All right, so this is your example for numerical example for the interval sensing. Now we will discuss the R code for interval sensing. All right. So we have this code. So in this code, we first define the values of L and values of R and their corresponding length. So here in C dot, we are combining the values into a numerical vector because of the C combine command. Here we create two vectors of equal lengths. L contains the left endpoints and R contains the right endpoints. Each row, that is basically Li and Ri, define an interval. All right. For example, for the first observation, it lies between 0 and 1. All right. And for second, it lies between 1 and 2, and so on. And in the length L, it returns the number of elements in the vector L. Assign that the number of n, basically the sample size. All right. So after that, we define the function for the each step, the conditional expectation, that is expected value of t given that t lies between L and R for the given value lambda. So here we have the expected t equals to the function. We are going to define a function of L, R and lambda where et is equals to the numerical length of L, and after that we are going to apply a for loop. All right. So function LR lambda define a function with three arguments. The code inside is the function body. Okay, this is all of these are the function body. This one also. All right. Et is the numerical length of L. It creates the numerical vector of zeros with the same length as L. This will store the conditional expectation. Okay. This one will store the conditional expectation. For I in 1 to length of L is a loop for each observation of the length 1 to length L. It will generate a sequence from number 1 to the number of the observation, and after that we apply inside this loop we apply if else condition. So if each dot infinite of Ri means we are going to check that whether the right endpoint is infinite, that is right censored observation. So if each dot infinite, this command each dot infinite will return the true if the values is infinity or minus infinity or a right censored observation. That is means interval is Li to infinity. All right. So after that we have the each step here. So derived from the properties of the exponential distribution that we already derived. So in the right censored conditional expectation, that is expected value of t given that t is greater than L, is basically L plus 1 upon lambda that we have discussed in several problems of EM algorithm earlier. So this code uses Li plus 1 upon lambda, capital Li plus 1 upon lambda. All right. And if it is right censored means observation if Ri is infinite, otherwise in the else. All right, we have the function formula that is expected value of t given that L sorry t lies between L and R, so that was equals to L plus 1 upon lambda minus R minus L divided by e raised to the power lambda R minus L minus 1. So we are compute this first we compute the width, that is Ri minus Li, and then we kept it in the formula that is ETI. All right, equals to Li plus 1 upon lambda minus width divided by the e raised to the power lambda into the width of the interval minus 1. All right, so it will return a vector of ET. Here, return ET will returns the vector of expected values. All right, so likelihood under the interval censoring we will discuss here. So that is log like interval, that is we defined as a function. Okay, of LR and lambda. Here we are taking LL equals to 0. So this is initializing the log likelihood accumulator, and after that we have for loop that is going 1 to up to length of L. All right, and in that one P equals to e raised to the power minus lambda Li minus e raised to the power minus lambda Ri. So that is for the exponential distribution. Probability that t lies between L and R is basically equals to e raised to the power minus lambda L minus e raised to the power minus lambda R. So that will compute the exponential function for that probability that t lies between L and R. And after that we compute the log likelihood, that is LL plus log P. It will add the log of the probability to the total log likelihood, and log L is the here normal natural logarithm, and it should return LL. So return the likelihood value here. Return LL will provide the returned value of the log likelihood. All right. So after that EM algorithm, how we are going to define this? So This is the EM exponential interval function of LR. Lambda initials value is equals to 1 and tolerance limit is 1 e raised to the power minus 8 and maximum iteration is 1000 and then start the function. All right. So here L and R are required data vectors. Lambda initial is the initial guess for the lambda. Basically default we took as equals to 1 and tolerance is basically the convergence tolerance that we have taken by default, that is 10 raised to the power minus 8, and maximum iteration is basically the maximum number of iteration, how much time we are going to iterate, that is basically up to 1000 times. All right. So after that, lambda old is basically equals to the lambda initial. Here it will store the current estimate value of lambda and history is data dot frame. So in that one, we create an empty data frame with 3 columns, iteration numbers. All right, lambda's estimated value, log likelihood value, and integer and numeric will create empty vectors for the specified type. All right. So after that, we have the for loop for the each step. Okay, so ITR, ITER in 1 to maximum iteration, that loop up to the maximum iteration time. All right, and in the each step we find out the E underscore head equals to expected value of T L R lambda old. So call the previously defined function to compute the conditional expectation given the current value, and in the m step we have lambda nu equals to length of L divided by sum of T hat. All right. So for exponential distribution, the MLE of lambda under the complete data is n upon summation Ti. Here we replace the unobserved Ti by their conditional expectations, that is Ti cap. All right, and we are going to take the sum of that expected values of T, and in LL we have the log likelihood, okay, with LR and lambda nu. So it will compute the observed data log likelihood after the M step. All right, after that we have the going to save the history. So history is equals to R bind. In that one we have the history data dot frame and our defined variables. So here R bind combines two data frames by row, and data dot frame creates a new one row data frame with the current iteration value. This appends the new row to the bottom of the history. All right, and after that we are going to print by the command cat. So concat net and the print text numbers. So we are going to print it, the iteration and lambda's value, and we are going to uh, return the values up to the 6 decimal places, and slash n is adds a new line, and after that we have the convergence check. So if absolute value of the difference of lambda nu minus lambda naught is less than tolerance limit, it should break. All right. So otherwise it should return the lambda hat equals to lambda nu, and it should store in the history. All right. So it will give the absolute difference, and it if the change is smaller than the tolerance limit, the loop should stop, break, exist from the for loop and update. After that, lambda new equals to lambda hat equals to lambda new here. All right, prepare for the next iteration, and after that we have return list. All right, that is basically returns a list containing the final estimates of the lambda hat and the iteration history. List can hold mixed type. Here both elements are named. All right. So after that we will run the EM algorithm. So in the results equals to EM exponential interval. All right. So we call the EM function for the example data and initial value lambda equals to 1. The returned list is the stored in the variable results, and cat prints the message, and result dollar lambda hat accesses the lambda hat component of the list, and slash n adds the blank line for readability. All right. And display the exact figure times at the final estimate. So we have T final, that is the expected value of expected underscore T, that is LR results dollar lambda hat. So it will compute the conditional expectation using the estimated value of lambda, and print we are going to use to display the vector. Okay, that is our T final. After that, we are going to plot the convergence of the lambda. So here we have the plot results dollar history dollar iteration comma result dollar history dollar lambda. So plot creates the scatter plot, and result dollar history dollar iteration and the result dollar history dollar lambda are the x and y coordinates. And type B we are using here, this is for the both points and the line, and x lab and y lab and main is the axis labels and the main title, and expression we have hat lambda. So it will produce the Greek letters lambda with the hat. Okay, that is the basically the mathematical notation we have. Okay, and after that we have the plot uh, log likelihood across the iterations. So it will be plot results dollar history dollar iteration and results dollar history dollar log likelihood instead of lambda. All right. So similar to the previous plot, but now using the log likelihood column, and shows how the observed log likelihood increased monotonically with the EM iteration method. All right. So that is the your entire code. Now we will run it and check what is the output. So first we check, we run the entire code here, and we find out this is the after the sixth iteration we got the convergence. Okay, the sixth iteration we got the convergence. We were getting exact convergence in the fourth iteration only. So the final estimated value of the lambda was 0.4054651, and the expected failure time at final estimate, that was for each values that we don't know in the initial. So that was 0.466035, 1.466303, 2.466, and so on. All right, these are the your values of capital T. And after that, we check the plot. So this is the convergence plot of EM algorithm. So we were getting the convergence at the fourth iteration, and we just checked up to the sixth iteration. All right, and the second plot was for the likelihood. All right. So similarly, at the fourth one, we are it is going to be converged, and it is monotonically increasing. So that is the your likelihood log likelihood plot. All right, and the maximum value is here of your likelihood. All right, more than around -10. Okay, so that is your likelihoods value. That was the R code and the example for EM algorithm with exponential distribution under interval censoring. In the next lecture, we will discuss about the EM algorithm for hybrid censoring. All right. So if you have any doubt or any comment, you can write down on my YouTube channel. I will reply for all your doubts and queries. Thank you so much, and All the best. We will meet in the next lecture. Thank you so much.